Okay, good morning. I'm going to try to introduce some of this chapter 15 ideas, work through some double integral problems, and get started on this new. It's the last major chapter that we're going to cover since we're not getting too far into chapter 16. So this is the last big idea is what happens when you do integrals, antiderivatives, when there's multiple variables. Starting with two variable situations, and what does that mean? And how do you work them, and how do you set them up, and what kind of problems can you do with that geometrically. And so we'll have some good pictures in here. Regular integrals are over an interval. If you're integrating dx, then you have some interval on the x-axis. When you have more than one variable going into it, you have a two-dimensional region that you're integrating over, and that's where it takes a little bit more work thinking that through and setting it up right. So I want to talk about some of those lead-in problem here, and I'll work some stuff either in the homework or similar to the homework problems that you're working on from the beginning of chapter 15. So if you got particular ones there that you're stuck on, let me know. I'm going to get started with something that's a regular integral just as a point of comparison, and we'll go from there. Just ready to go. Okay, so I wrote this one down. That's not a double integral. So I wrote this one down. Just a regular integration problem, but it happens to have another letter sitting in there, that h. But you notice when we're integrating with respect to x, x is the variable going on. So that means a couple of things here. The x value here means that these are x values over here that we're going between, usually just numbers. So we could write that x equals with those. And it means that the other stuff isn't changing. We're slicing up the x-axis between 0 and 3 and taking different values of x across that interval. Nothing else is changing with this. So the other letter that's in there, we have had some problems like that where there's extra letters going around. And we shouldn't get thrown off by that. In this context, the h is just a constant, right? So your antiderivative should just be with respect to x, and that h is just, or h squared here are just constant multiples of these terms. So we take the antiderivative just with respect to x. So the antiderivative of x is x squared over 2. This times h will just be along for the ride here. And the antiderivative of negative sign here is positive cosine. Actually, this constant multiple doesn't do anything. And when we evaluate that thing, these x values are going in, the h is still going to be there. So we're going from 0 to 3. So we plug in the 3, h times 9 over 2, plus 3h squared cosine of 3, whatever that is, minus, this would be a 0 term, and this would be a 3h squared times 1 term. So we'd have those values, and we'd still have the h in there, and it really never entered into the calculus or the evaluation parts of any of that. It's just a constant that's along for the ride. Now, if you can handle that in that context, we've got to set up these others and think about them the same way. We're going to have two variables, but we're actually working these problems with one variable at a time. So they're going to have usually x and y for these rectangular coordinates problems anyway. The two variables are x and y. We've got to solve them by looking at it one at a time here, integrating with respect to x and integrating with respect to y. That's what we're going to be seeing now. And the other one you've got to treat as a constant, just like we did the h in here. So you'll see this strange looking notation. Strange until you get used to it. There's a couple integrals, some kind of letter down here, some kind of function of two variables in here, and it might start off with the dA sitting right there. capital A, for area. Now, our old integration, this was the variable that we were looking at. Integrating with respect to x meant we sliced up the x-axis into little pieces and used x values in between there. In this setting, this is the symbol that means that we're slicing up the area into tiny little pieces of area. So you could actually go through the whole subdivision argument and look at slices of an area right there. I'm not going to spend a ton of time on the theory of it, but basically this D that's over here that we're integrating over, or this is the region, isn't going to be just an interval anymore. It's a subset of the xy plane. It's a set of xy values, so it's some subset of the xy plane. So if you have some box over here in the xy plane, then we're slicing that thing up, and the little subdivisions of area would be like that. Each little subdivision of area would be a little dA thing. Now the area is just multiplication of length times width. So you could look at that as slicing up the y values and slicing up the x values. And this is going to be dx times dy. Now that multiplication is kind of formal right there, because really we're talking about these things approaching zero, the change in x and the change in y. But that's how you get area, is just multiplying those. So this is going to become just dx and dy in some form. And so we're going to rewrite this integral. It's still a double integral of this function, but we're going to rewrite the dA as dx dy or dy dx, whichever way around is more convenient. You got choices right there. And that means these two integrals are not a single symbol anymore. They're two different symbols. And we're going to integrate. If I set it up this way around, then the y from this dy means these have to be y equals something, and we're just doing an integral with respect to y. So I'm going to throw this big grouping symbols in here, because that's what we mean by the double integral now, is just that inside here I've got an integral with respect to y, where the x is treated as a constant. And then once I'm done with that, I'm going to substitute whatever's here for y, and I'll only have a function of x left from all of that. So I'm going to have the integral of something with respect to x, where x is the only variable going on in here, and these are going to be x values, numbers out here. Now, if we have a rectangle like this, this is the first section in the book, is just dealing with rectangles like this, where if this is from -5 to -2 for y, and from 0 to 4 for x, then these can be just interval things. The y then is going from -5 to -2, and the x is going from 0 to 4. So we could even put those in right here. If they're all numbers, you're dealing with a rectangular region. It's just an interval. Well, it's the cross product of an interval with an interval. It's a set of ordered pairs right there. So if you're into cross products, that's what we're dealing with there. Not a vector cross product, but the set cross product of those two things. Anyway, we just deal with them one at a time. If they're just intervals, then that's fairly easy to set up. You got to keep track of what number goes where and which variable you're dealing with at a time. So hopefully you've formed good habits of linking in your mind the integral symbol with the d whatever that's over here that you got to keep track of, because now we got two layers of that to think about, and we got to make sure things stay aligned right. If the dy is the first one in our list, then the first inside integral over here is an integral with respect to y. So whatever you put on here has to be y equals something. Now, as we go along, that's not just going to be y values as numbers, but these can be functions of x that we go to and from, because we could have functions of x here that we plug in to this, still end up with a function of x here. So when we're doing the inside one, we treat x as a constant in the integration. treat x as a constant in this thing. And when we get down to here, there shouldn't be any y's left because we're substituting things in for y. It's a definite integral. We're substituting those things in for y. So there isn't any y's to deal with in this. This is really just a single variable integral that we end up with at that stage. That's how we're going to think this through. So these that we're integrating to and from and to right here can be numbers, but they can also at this stage be functions of x. When we get out to here, these really need to be numbers that we're starting and stopping them. So we're kind of going along in the picture some particular slice of this. Whatever x value you have, you're treating it as a constant, and x just sits there, and we're integrating along this whole slice as y goes from -5 to -2 on that whole slice. And then when we get to the x stage, that's when we're going to move the x's across to make sure we get everything across that dimension. So I do some examples on that this morning. If you get more than just rectangles, then it's a little more work in setting it up. And that's what we have to get used to, is looking at that region there. It might not just be a rectangle, could be a more interesting region. And then we got to think that through. Going on with that. Sometimes the way that they present the description of that region makes it a lot more interesting. Also, trying to understand what's going on and visualize it properly. Let me start with a straightforward example, and then I'll try to work some of the more interesting ones as well. So from 15.1, I'm going to do number 27 out of the book right here. That's a regular double integral over. They actually use an R for it here over a region, but in this case, it's just a rectangle. It's x secant squared y. So there's your function, and that dA thing means we're talking about subdividing area in this region, but they have to tell you what the region is. And for this one, the R that we're dealing with is x values between 0 and 2, and y values between 0 and pi over 4. So those are the inequalities that define the region. That's what we're looking at. That is just a rectangle right there. We could draw a picture of it. I don't think it would be very helpful on this one to see the picture. We do have a function that has discontinuities, has asymptotes at certain values. This is undefined if we get out to whenever cosine is 0. So that's like pi over 2 or minus pi over 2. We would have a function that's going to infinity right there, but that's not bothering us within this region right here. So we are within the domain of the function. It's a nice continuous function inside there. So there's anything to worry about with that. Just got to set it up and work through it here. And I have a choice to make right away. I believe this one would work out fine either way, but my choice is which one of these things do I want to put inside and which one do I want to put outside. I want to deal with this function. This would be pretty easy to do the antiderivative with respect to x, because this would just be a constant, and the antiderivative with respect to y, this would be a constant. So neither of those is going to be a hard antiderivative. That's one of the things to look at when you're deciding. I'm trying to decide which way around to do dx dy or dy dx. I think this one would work fine either way. Sometimes that's determined by the shape of your region and what boundaries your region are, but sometimes it's defined also by what do I want to deal with as far as taking an antiderivative here? What does the function look like? Which one would be easier to do first? In this case, it's going to be fine either way. I'm just going to throw these down. I guess I'll do x, y. You set it up as dx, dy. You're putting the dx first. That means that's the one you're going to deal with first. And that means I need x values here. And here my inside integral needs to be x values. So that's going from 0 to 2. And no matter what x is, y is always going from 0 to pi over 4. So those would be on the outside integral because that corresponds to the variable on the outside thing. So that's what we really have to get used to, tying these things together. And of course, you also have to remember all your integration stuff that goes along with this. I think they're usually pretty nice about the function, but we got to remember how to do all the antiderivative stuff that we haven't thought about for a little while here. And I also have to get used to thinking of secant squared y as just a constant sitting there. So really the function that I'm dealing with is just a constant times x. So it's the constant times x squared over 2 is the antiderivative. Very similar to what I did with an h sitting there. It was just the function of x is simple. Functions can get more tangled up. The x's and y's in the function, but in this case it's just multiplied by the other one, so this is constant multiple when we're dealing with the x. Now before I can go on from there, I can't have any x's left. There's an x left, but that's because I haven't done this yet, right? This is the antiderivative. It needs to be evaluated from 0 to 2. You really have to do definite integrals with this. There's no general antiderivative of a two-variable function. It's one at a time, and it's based on the region that it's in. So we're just dealing with definite integrals on this. You're always going to have stuff to put in for it. And plugging those in for x, I get 4 over 2 minus 0. So I just get 2 secant squared y. Integrate between 0 and pi over 4. So now it is just a regular single variable antiderivative problem. There isn't any x's left in it now. Antiderivative of secant squared is tangent. So I got 2 tangent y evaluated from 0 to pi over 4. 2 times tangent of pi over 4 minus 2 times 0 is just 2. So that's 2 is the value of this integral. What that represents geometrically there is 2 units of volume. Really, we had a box in the xy plane and we had some function over top of it, some surface going over that. And this adds up all of the volume under that surface. I put the under in quotes because I really mean it's we're looking at the between the surface and the xy plane. This is a positive function, so it is under the surface right here. It came out to nice positive volume because this function is positive everywhere in this region. If it dipped below it, then we might actually get negative volume if our surface is below the xy plane. That's the same kind of considerations that we had with regular integrals. Just a three-dimensional picture that goes with it now. All right, kind of a start on one of these that I put in the homework that I had to stop and think when I read it, looking ahead, or looking at it this morning. Number 43 here. Ask for the volume of the solid enclosed by the paraboloid and the planes z equals 1, x equals 1 and negative 1. Y equals 0 and y equals 4. Those are all planes, but they're the boundaries of our region. Now, all of this stuff takes place in the XY plane. That's just a regular rectangle like we're used to looking at in this section. X is going from negative 1 to 1. Y is going from 0 to 4 on the y-axis. So we're talking about this rectangle R right there. This is the plane up above them, the z equals 1. So the way that that's phrased is a little strange. We're trying to find the volume between this surface and this surface. The plane z equals 1. That's z. So what I thought when I looked at it, if I'm going to do volume between two things, then I need to look at where they intersect. And if I try to look at where they intersect, where z is equal to this is equal to 1, then I'm looking at where 2 plus x squared plus y minus 2 squared equals 1. And that looks like some kind of circle thing. And I'm a little afraid about how complicated that's getting. But it turns out that this is nothing at all, because x squared plus y minus 2 squared is never going to add up to negative 1. So if I simplify that down, it's not a circle. There's no such points right there. So that's telling me that these don't intersect. There is no intersection between this surface and this plane. And if I look back at it, that's because this is 2 plus a bunch of positive stuff. Z is always above the surface. This is entirely above z equals 1. So we got some paraboloid up here. I can try to make some picture of that, but some surface up here in the plane z equals 1. It never gets down to it. This is a paraboloid going from 2 on up. So we're talking about a volume above this plane up to that surface with no intersection point. So it does cover this whole region, but the volume between them would just be the top minus the bottom right here. So over this region, I have to integrate this function minus this function. That would be the top boundary of my volume, and this would be the bottom boundary of the volume. So I'm integrating in between there. Instead of going all the way down to the xy plane, I'm going down to z equals 1 instead. So I'm just going to have a minus 1 in the setup right there. It seems like a lot of extra stuff, but all I'm doing is the integral over this region of the function minus 1, because I'm cutting off that bottom part of the volume. So that's all that's going on there to set it up. Put my z in here, my function in here. It's that function minus 1 that I want to integrate to get the volume above that plane. So this is the volume of the region. Top minus bottom is what's going on. In this one, you could do this either way around, because the x and y are kind of on separate terms. You're going to do one at a time. Really doesn't matter which way around you do it. If I decide to go dx, dy, I just got to get the right numbers in the right places. So that means the inside one is dx, going from negative 1 to 1. And the outside one is dy, going from 0 to 4. So you got to make sure you get those in the right place and keep track of which values is which. You can finish that one off. That's the setup on that. Now, more interesting regions, some of which we'll even get into using polar coordinates for the region. So more work to those. And they talk about type 1 and type 2 regions here. You need a region that either has a top and a bottom function, or a region that has a left and a right function that you can set these up between. So done some of that stuff before with integration problems, like in the solids of revolution and things like that. That's everybody's favorite thing to do. I know this is comparable to that, in that you have to work through the picture of it to kind of get the integral set up right. What do I put on as bounds of the integral to do this. So you got ones like number 7 here. I'm going to get started with the setup on number 7. This is from the second section, 15.2, number 7, where it gives you inequalities, and that's kind of a nice setup for it. So it starts off, they use capital D for more interesting domains if it's not a rectangle. So that capital D is going to be described here. We're integrating over the area where D is given by this. X is between 0 and 4. Y is between 0 and the square root of x. That's exactly the inequalities written down. So it's telling you x is going from 0 to 4 and y is going from 0 to the square root of x. Now that's where it's not a rectangle. It's following some curve right there. I could draw this. It's probably a good idea to draw this, but it's laying it out for me that since y goes between functions of x, this is the top function, top in the xy plane, and this is the bottom in the xy plane. So I need y to go between functions of x, and that means when I go to set up this integral, I need that function of x in here. I need the dy to be the inside one, and then x is the numbers. I'm going to need numbers on that outside integral, so this has got to go to the outside integral. And this can go on the inside integral. You can have functions of x on the inside integral if I deal with the x later. Tying that to the picture, from 0 to 4 is what's happening for x. From 0 to the square root of x is the curve on this thing. This is my domain that I'm looking at here. So top and bottom function going on. This is where y equals square root of x. That's a terrible drawing of it because it really goes more like this. Okay. That's y equals square root of x between those things. So when I do y, it's going from 0 to square root of x. That's the deal. And so that's got to be the inside integral. And the 0 to 4 has got to be the outside integral for x. That's the thing. Now that means we're going to be substituting in stuff like that for y after we do the antiderivative. We're evaluating it from 0 to square root of x. So that's where there's a variable floating around out here, which we're not really used to. But the antiderivative with respect to y, this is really just y times some great big constant, 1 over x squared plus 1 is just a constant, times y. And so the antiderivative is just y squared over 2 times constant again. Still haven't done this, so I got to copy those down. This is the antiderivative, so I've done this integral, but I need to evaluate it from 0 to square root of x. And that's a little weird to have a variable floating around in that thing, but the inner integrals of these multiple integrals, that's what's going to happen. Oftentimes you're going to have functions there, maybe for both of these things. As long as they're functions of just this letter that I still have to do, that works out just fine. Substitute those in for y. That's square root of x squared over 2 minus 0 squared over 2. And so that's x over 2, I guess I get out of all of that. That's disappointing, but it's only disappointing to me because I like inverse tangent stuff. This doesn't end up being an inverse tangent thing. It ends up being something I can do. There's a 2 sitting there, the 1/2. I might actually just move to the outside. The 2 might go out there. But this ends up being something you can do by u substitution instead of having an inverse tangent form there. It's a u substitution instead. And we'll get a log form of something from that. So you can finish that off. The setup there is illustrative of what's going on with this. So we have to get used to this inside integral being from a function to a function, and the outside integral being from a number to a number. That's the types of regions we can handle. And if it's top and bottom situation, then it's functions of x, and these are y values. And if it's a region that's better described using the left side and the right side, then those will be left and right in here functions of y, and these would be y values, and your letters would be the other way around. So that's the other situation. Some of them could be done either way. A lot of these things actually could be worked in either direction. Go through some of that. I'll look at number 18 in here. Starts off looking like this, and I worked through this one ahead of time, so I got to think about this. But I believe I can set it up either way here. We'll see what this XY plane picture looks like. That's the big deal with these, is getting the right picture of what this domain here is in the XY plane. For this one, it says D is bounded by y equals x cubed, x equals 1. Region bounded by those three things. So whenever I see bounded by some stuff, I start thinking, where are they equal? Where do they cross each other? Because that's going to be interesting points. Let's see what that looks like on the picture then. Simple sketch. Y equals x cubed. These do intersect at some points there, so those look important. And x equals 1, which is right here. So wait a minute. What's bounded by all of those things then? Okay, copied the problem down wrong. I'm sorry, I grabbed something from another exercise right here. That does not say x equals 1. That's from a different problem. It says x is greater than or equal to 0. So this line, this cubic, and where x is greater than or equal to 0 means we're just doing this little piece right in between here. So that is where x equals 1, but that's where it ends up. We're going between 0 and 1, between these two curves. So I got a top and a bottom again. Top is y equals something, a function of x, and the bottom is y equals x cubed. So I could set it up this way. If my top and bottom are functions of x, then I got to go from bottom to top. I put those in wrong. From the bottom to the top. And the x values are still going to be numbers out here. That means this is my integral dx. And the inside one is my integral dy. So it's got to be that way around. And the function, again, we're dealing with pretty easy function to do antiderivatives of. But the setup is the hard work on it. So antiderivative with respect to y, you're thinking about first, that's going to be y squared. This is just a constant term, so the antiderivative would just be x squared y and y squared, and so on with that. I want to think about setting that same thing up the other way, because a region like this also has the right and the left side that are separated. The cubic there, y equals x cubed, is also the right side of this thing and could be written as a function of y. X equals y to the 1/3 is that curve, and the left side of that thing is the line y equals x or x equals y. Since I can write those both as functions of y, I could do this as a left-right thing and set it up very different looking. If I go with left and right as functions of y, then I'm going from left to right. And that's got to be my dx integral. So dy is on the outside. The y values are going from 0 to 1. The y-axis, those would be the numbers out there. Function still sitting in here, but I'm doing the antiderivative with respect to x next. So that's going to look quite a bit different at the next step, because antiderivative with respect to x of this thing is x cubed over 3. This constant term, the antiderivative of a constant, is just a constant times x. That's going to be evaluated from here. So that looks like a very different problem now than what you would have had here. But there are just two ways of setting up the same thing. Let me get this on the screen. That's what that ends up looking like. And so for a problem like that, I could have done, I can do it as top and bottom or as left and right because of the geometry of that little sketch right there, you know, what the region looked like. And if you go with left and right functions, then it's going to be a dx dy. And if you go with top and bottom functions, then it's got to be a dy dx thing, because these are the bounds of the integral. So that's the contrast between those two. Function would have been fine either way around, but the region has to be described one way or the other. And in simple cases like this, you can pick either one as long as you set it up the right way around for that. So you want to get a good sketch as you're working problems in here. You want to get a very good sketch of what this domain that we're looking at is, what it looks like in the XY plane. I'm not even thinking about the three-dimensional picture here where there's some surface over it. I don't really care what the surface is shaped like, but the shape of this region is very important. Getting the domain graphed right, because I got to decide whether to go top and bottom or whether to go left and right, and which way I'm going to go with that. So if your region is set up with top and bottom functions, that's leading you toward a dy dx setup. And if your region is set up with left and right functions, nicer, then that's going this way around. And this is the kind of region that could be done either way. Some of these would work fine either way. I'm going to go ahead and jump to one of the 15.3 exercises. Try to set it up using this same process. We're going to run into a problem with that, and that's when we have to resort to polar coordinates. That's why it's in 15.3. But we'll look at another one of these domains and think this through. I'm going to grab one from here. It's 15.3, number 11. Again, double integral over a domain, function of x and y. It starts off with dA, same kind of problem. R is the region that lies between R. D is the region bounded by the semicircle x equals square root of 4 minus y squared, and the y-axis. So x equals square root of 4 minus y squared is part of x squared equals 4 minus y squared, so x squared plus y squared equals 4. It's a circle of radius 2. But it's a semicircle because x equals just the positive square root of that. So we're only dealing with the positive x values. Dealing with this semicircle where x is positive on the circle of radius 2. And the region bounded by that and the y-axis is the entire semicircle then. So that's the region that we're looking at. It's got a pretty clear right side and left side. It looks like a right side and left side thing. You could do top and bottom, but top and bottom are chunks of that circle. So you'd have to go from circle equation to the minus part of that circle equation, and that would be a pain. This is a lot nicer set up as a left and a right. It's got y-axis, x equals 0 as the left side, and it's got the semicircle x equals square root of 4 minus y squared as the right side. So it's a good left-right setup from this domain. So I could set it up this way using x and y, using the left and right thing. Now, if I'm going functions of y, then the x has to be the inside thing, and the y has to be the outside thing. I need numbers for y, but I can tell what numbers the y goes to and from here because that's where these intersect. Here is at minus 2 and 2. And x is going from, well, it's from the left to the right here. So all looks good with that. I'm pretending this problem was in 15.2 and setting it up as a double integral over a regular domain. There, that looks good as a setup for that thing. That would integrate that function, that surface, over that whole domain. No problem, except there is no antiderivative of that function with respect to x. So the setup worked great, but trying to integrate that with respect to x is not going to work right. This kind of function, if I'm doing antiderivative with respect to x, you're not going to get a nice antiderivative to that thing. Not the kind of function that has a nice antiderivative. So that's correct. Setup, that value would be the right value, but actually working the problem that way is impossible, not because of the domain, but because of the function. I don't have an antiderivative with respect to x of that thing. If I did, I could plug this thing through, but I don't. So that's why in this one we're gonna go to polar coordinates instead. So we're gonna take that same picture but reinterpret that in terms of polar coordinates and set it up that way. That's why we need polar on this one. Should be able to do it somehow. So instead, we're going to take that same picture, same semicircle, and put the polar equations down that we're dealing with. All of this stuff is the same. This is just the circle r equals 2, right? X squared plus y squared equals 4. Means r squared equals 4. R equals 2 is that circle. And the region bounded but by that in the y-axis, that can be taken care of by thinking we're only going to do the part of the circle from here around to here. Theta equals 0 here. We're going from theta equals minus pi over 2 to theta equals pi over 2. And that'll take care of this part. That'll sweep this thing out from minus pi over 2 to pi over 2 in these little chunks of theta and the little chunks of r going this way. So our little area pieces are shaped a little different here. It's not just a little rectangle anymore. It's a little sector of piece of a circle here. It's a little chunk of a sector of a circle, so the area formula is a little bit more complicated. And instead of dA turning into just length times width dx dy, it turns into, well, a little geometry there, but this little chunk of area, this little dA here, turns into the area formula for that is actually r dr d theta. Now, these are interchangeable. It's got to be times r. So the r just gets multiplied by your function here, and we're going to integrate it. These are interchangeable. The r is part of the function now, and these are interchangeable. Usually the d theta is done last, and that's going to work nice for this one because I have constants for theta. That's typically the outside one with a polar, not always, but usually with polar, you're going from some angle to some angle, and you got your outer and inner radius, or the single radius equation on the inside. So theta being the outside one works nice on S. Minus pi over 2 is where I start, and pi over 2 is where I stop. R goes from the origin all the way up to the circle, r equals 2. So those end up being constants in this case anyway. My function needs to be written in terms of r and theta then. But this, e to the minus, if I put the parentheses in there, is e to the minus r squared. X squared plus y squared is r squared. So I'll make the substitutions to get this function written in terms of e, in terms of r and theta. In this case, it's just my e to the minus r squared. So I converted everything to polar form. And you have this times r in there. And that's what saves you on a problem like this. That's what makes this doable. So there's no antiderivative for e to the minus x squared, but there is if you can do a u substitution, if you have the r out here. So now we're set up to be able to actually do an antiderivative of that with respect to r. I'm thinking of this thing now. Forget about the theta for a minute. Deal with just the r, but now I'm set up to do a nice u substitution. That u can be I guess I'd really rather deal with just e to the u, so I guess I'll let u equal minus r squared. Yeah. Just doing a u substitution, I'll have this. So this is minus 2r dr, which is kind of what I have sitting there. So that makes this doable where it wasn't in rectangular coordinates. Copy down the part that's not changing, that I'm not thinking about yet, which is my outside integral. This one, I'm not doing the integral yet. I'm just making the u substitution now. R dr becomes du. That negative 2, I'm going to have to do negative 1/2 du. So I'll put the negative 1/2 on the outside du. That's dr, and this is just e to the u now. Now I did a u substitution. I like to go ahead and change the limits of integration when I do a u substitution so I don't have to come back to that letter. So I got to think about where these things go. R was going from 0 to 2. That means u is going from 0 to minus 4 now. When r equals 2, u is negative 4. That's going to be up here. Those are kind of backwards, but that's all right. I could reverse them and change the sign if I want to, but I don't really need to work that out. Now that's an easy antiderivative. Antiderivative of e to the u is just e to the u. So I'll have negative 1/2 still. Antiderivative is just e to the u. Evaluate that from 0 to negative 4. And then I'll work on the d theta part. Let me finish this one off, I guess, since I'm this far along with it. That's going to be negative 1/2 e to the minus 4 minus negative 1/2 e to the 0, which is 1. So that's a plus 1/2. Integral of that, but it's all just a constant. I don't actually have a function of theta. I have a constant function of theta. So antiderivative of this big constant, which I'm simplifying a little bit here, that's positive 1/2 minus 1/2 e to the minus 4 is my constant. Antiderivative of constant is just the constant times theta. And then I'm going to evaluate that from minus pi over 2 to pi over 2. So this minus that is pi. And I've got pi times 1/2 minus 1/2 e to the minus 4. That e to the minus 4 is tiny. This is a positive quantity, which I would expect on a positive function over a region like that. That's a volume over this region of a positive surface of some sort. So I expected a positive value at the end, and I have one. That's good. So that's a fairly simple example of this stuff using polar. The things to remember with polar is this is going to be r d theta all the time. The r is part of the function that you have to integrate right here. You almost always do the integral with respect to r is the first one, and theta is the outside one. Almost always with polar, because polar you're writing r as a function of theta, and almost never the other way around, right? R is a function of theta is polar stuff. So the boundaries are usually going to be functions of theta. They might not be constants, or here they might be functions of theta, and that's going to work okay if you're doing the d theta last. So that's typical for how these things go. That was like one example of each kind of thing, and they're time consuming, and I didn't even finish all of these problems. But you got some other examples out there in the in Lumen work that are done, and got to get used to the setup here, and you got to get good with little sketches and thinking of the little sketches the right way. A little bit more complicated than integration problems were before, because the extra variables going around. So try some stuff out. Get some questions to me during the week as they come up, and we'll keep in touch. Have a good day.